Professor Valentin Troll.
Thank you so much, Robert. As always, you're too kind. I would like to talk about the Atlantic. And this is one of my, well, personal favorite talks. It's a little geological, but I'm sure we'll all get through. And there's something funny about this talk I realized this morning. The funny thing is that whenever I give that talk, the sea seems to be bumpy. Maybe it's because they always put the talk on a sea day, but I also realized I always wear my blue tie on that day I give that talk. Maybe it's actually the tie that makes it so. Anyway, we are sailing the Atlantic. We have been in Iceland, and we're coming back towards Europe. And yeah, this makes me think about the Atlantic as an ocean. The Atlantic is actually a little youngster when you think of the seas of the world. And it's the second largest ocean despite its young age. It covers about 20% of the Earth's surface, and about 29% of the Earth's water is actually contained within the Atlantic. So despite its geologically young age, it's quite a serious ocean. So the Atlantic, well, here's an image. This is an image where the water is drained away, and you can see this spinal cord in the center of the Atlantic. And this is the mid-Atlantic ridge. It goes all the way from the very top in the north to the south. And this ridge system spans through the other oceans as well, actually. This mid-oceanic ridge system is going through all the oceans globally. It's coming up to a total of about 60,000 kilometers, of which only a fraction is in the Atlantic. And it divides the plates. This is the spreading ridge in the Atlantic, and it spreads at a comparatively small rate. And this has been going on for quite some time. So it's, as I said, a relatively young ocean. And just to give you a flavor, the United States is less than 1/6 of the size of the Atlantic Ocean. So it's a big piece of water. And the Atlantic is, as I said, the youngest because it started to spread in the Jurassic period. That's, as you all know from Jurassic Park, that's when the dinosaurs were around. This is when the Atlantic started to spread, and it started to spread in the south. South America and Africa were starting to spread, and then like a zipper it went further to the north, and it reached the northern part in the Cretaceous time, and it's still spreading ever since. So it started about 180, 150 million years ago, and it's coming from the breakup of a supercontinent. We have learned about supercontinents only comparatively recently. Only in the last 100 years have we understood that the Earth has tectonic plates and they are moving around. And every now and then in Earth history, all of the plates, all of the continental masses come together and they make a giant supercontinent. And the last one we had on the planet was Pangaea. Some geologists argue there's supercontinent cycles, and there has been supercontinents prior to Pangaea. This is very far in the Earth history, or down in the dark periods of geology, and there were other supercontinents. One of them was called Rodinia before Pangaea, but maybe we're going a little far here. Let's go back to the Atlantic. So the Atlantic and the breakup of Atlantic, this is something that this gentleman here pioneered. He was pushing the idea of continental drift already in the 1920s and 1930s, and he got a lot of grief for it. This is Alfred Wegener. He said, if I take South America and if I take Africa, I can actually put them together. And if I take North America and the European margin, I can also fit them together. And he came up with this concept of Pangaea. Pan, everything, Gea, Earth, the entire Earth in one mass. That was his proposal. And not only did he say, look, they fit together like a jigsaw, he also pointed out that there's different types of fossils in different places, and they also match the jigsaw. This was very important. It's not just that land masses seem to fit, it was also that rock types and fossils on either end of this jigsaw did actually match. So this was an important realization, and he came up with this concept of continental drift. The biggest criticism he got was for a lack of a mechanism. He could not actually, back in those days, understand why the Earth was doing this, and academics, well, you know, they can be a bit uptight, and many of them said, yeah, that's all looking great, but you don't actually know how this works. I make a big point of this. Whenever we have important observations, I make sure the observations are correct. Whether we understand how the observations come about, that's the next step. Observation first, understanding the mechanism comes later. So, a very important lesson from Mr. Wegener. And nowadays, he's of course a hero because he pushed this idea, and now it seems that this is the best model to explain the drift of the continents or the movement of continents. On the left-hand side here, we have a little reconstruction, Pangaea falling apart, and all the land masses drifting apart now. And for the Atlantic, we have new ocean crust forming every day, literally every day, and it spreads apart, and the red colors and the yellow colors, this is different ages of submarine volcanic rocks, and the youngest ones are, of course, in the very center. There we have the spreading zone, and there indeed, there is new volcanic rocks forming every day. So the idea of spreading is now explained a little better than in Wegener's day. We have this concept here that the Earth mantle is actually convecting. It's convecting at a comparatively small rate, but over geological time it makes a huge difference. And we have these three different types of processes. The one is the ridge, where spreading. Then we have subduction here at the margins. When plates get too old, they start to sink back into the Earth mantle. And then we have these anomalies, the plumes, the hotspots like Hawaii, the Canaries, and Iceland, where we have, like in a pot of boiling soup, we have these bubble streams coming up. But of course, in the Earth, this is hot rock. So this is the three main ways of making volcanoes, and a good, really mature ocean has all three of them. The Atlantic is a young ocean, as I said, and it's not doing so well on all three of them, but I'll run you through that now. Let's start with the spreading centers. So the idea here is that the plates are spreading apart, hot material is welling up, and close to the surface it starts to melt, and it makes submarine volcanoes. Can we test this? Yes, we can. Because when rock forms, there is a lot of tiny little magnetic minerals in there, magnetite and ilmenite, if you're interested in their names. And these are little needles, and they actually start to orient themselves according to the Earth magnetic field. And that means, depending on how the Earth magnetic field was at the time of formation, these needles have a certain orientation. We distinguish normal and reverse magnetic polarity, and you can measure this. And indeed, the ocean floor has stripes of normal and reverse magnetic polarity going back through time, and this allows us to identify different age domains in the ocean crust. This spreading concept is also verified by looking at other situations. If we look at continental rift valleys like the East African Rift Valley or the Rhone and Rhine rifts, and looking then at the Red Sea and to the Atlantic, we actually see different stages of how continents break apart and how the ocean comes in and fills this basin, and eventually a full ocean has grown like in the Atlantic. So we understand these stages, these life stages of continental rifting by looking at slightly different examples all over the planet. And of course, we've just been to Iceland, which is often cited as the archetype of plate spreading. Well, I told you before, there is a little bit of a helper, and that's the hotspot. Otherwise, the spreading center would be underwater. And in Iceland, we can see the spreading onshore. So here's an impression of the plates are breaking apart there, and you get a rift valley, a lower ground that subsides because of the spreading. And this happens at a rate of about 2 centimeters a year. This has been going on for quite some time, as I pointed out. It's been going on in the North Atlantic, certainly since the Cretaceous, and we have volcanic rocks from this process in Greenland, in East and West Greenland, of course in Iceland, but also the Faroe Islands, which we've passed just recently, and in Northern Ireland, and in the Scottish part of the British Isles. And we have some fissure intrusions that even go into England. In northern England, we find some rocks of this type as well. The situation in Iceland is particularly exciting for geologists because we have this plume that helps us and it pushes the ridge above sea level, making it possible for us to actually go and inspect this and sample the rocks. When we look at the spreading center, then here's a few impressions. On Iceland itself, it's going on for several kilometers. If you move towards the edge of Iceland, it starts to get filled with seawater because the ridge, the spreading center, continues underwater. And if you've been on the two legs of this journey, or only one, you would realize we have actually sailed above a submarine spreading center. We have actually sailed over submarine volcanoes. Most likely there was a little eruption, but they're so small and they're well confined, they're under a lot of pressure in the water, we wouldn't have realized that. But we have actually sailed over those spreading centers. Now here an impression close to the Icelandic coast, the water comes in and it fills these fissure cracks and these fractures, and of course people make a hobby of it. You can actually dive down there and you can look into these fracture zones. And the deeper you go, well, at some point your scuba dive gear doesn't do it anymore, so you will have to have different devices, but this kind of gives you a feel of how these faults and fractures seem to continue underwater. When we go all the way into the submarine realm, then we must realize the Atlantic Ocean is actually quite deep. The average depth is about 3,300 meters. The deepest point is actually close to Puerto Rico, where it's 8,600 meters deep, and we'll come back to this a little later, because that's a different phenomenon, that's not the spreading. So the mid-ocean ridges are usually about 2 to 3 kilometers deep, so there is a bit of a mountain range of about maybe a kilometer high mountain range on the seafloor, and this is where we have that spinal cord that runs through the Atlantic. When I was sailing as a research geologist, I was on various research ships, and just to make you feel good about the bumpiness today, I had some really nasty days on sea, so there's a few impressions there. You will not see something like this on this ship, so it's gonna be okay. And with these ships, what we do is we actually go right above these spreading centers, and we can either send down submersibles. That's easy, and they can grab rocks. They have these arms now. But the more traditional way, and this is what we did in the 90s, for example, is to throw out steel buckets, big steel buckets, and have them scraping over the rocks. And then we pull them up, and then we'll see what's in there. It's a bit like rock fishing. And there we get a lot of information about the rocks on the seafloor without having to actually go there. I remember as a very young PhD student, I was on one of those journeys, and we were actually having our first target out, and the bucket was scraping. You could see it on the monitor. The pressure was very high on, the cord, on the steel cord, and at some point the pressure drops, and the captain goes completely white, and we lost the steel bucket. So the cord snapped. And it's a huge financial disaster and a scientific disaster as well. And, the captain was not very happy, and we had to try again. We did succeed in the end, but it's quite tough work, and it's a lot of stress when you do these things. So, how does it look down there? We can use surface analogies. Here, for example, the Meradal eruption on Iceland, where we have a fissure cracking open and producing lava fountains. Underwater, there will not be fountains because the water pressure is too high. The lava is under more confinement pressure, and the lava flows. It will chill very quickly, and it usually stays more liquid inside. There's this wonderful phenomenon, you may have heard about it, the Leidenfrost effect. Have you ever had a drop of water dancing on a hot plate? I'm sure you've all seen that. And why does it do that? Well, you would think it evaporates immediately, but no, it doesn't, because a film of steam forms, a tiny little film of steam. This was described by Mr. Leidenfrost already in the late 1700s, and this is what happens underwater as well. You actually get a steam film, and it insulates the lava, so the lava can continue to flow, although there's a lot of water around it. So here's one of those submarine fractures in the deep part of an oceanic ridge, and it's very dark, of course, when you look in there. And this is right in the center of such a spreading zone. And here's some lava, and here you see that the outer crust has formed, and it's still liquid inside. And this is insulating the interior, so there you get tongues and pillows. They will form in these areas. And the equipment in the lower part there, that's actually from a submersible. What we also find is we find a lot of hot springs down there. There's different types. There's white ones and dark ones. For some bizarre reason, they're called white and black smokers, but there is no smoke on the ocean floor. They are actually zillions of little mineral grains that precipitate, and depending on what minerals are precipitating, you have either a black or a white color. So here's a few impressions from the ocean floor. Here's pillow lavas. These are called pillows because they are, well, rounded, but effectively they are tongues of lava that form underwater under the confinement pressure with the Leidenfrost effect, allowing them to continue to flow for quite some time despite an overwhelming amount of water being around. So here's a few more. Here's a mountain of pillows. And when they cool, they develop these radial cracks. In the top right, you see a few of those radial cracks, and sometimes they break out again. And here in the bottom right, we have a lava tongue that is breaking out of a pillow. So the interior was still liquid, and then it was moving out. And of course, within a short while, there's ocean life that's teeming there, and that's filling these pillows with all sorts of things in the interstices as well as covering the surface. So here is a submersible taking a sample. It's breaking it off, literally. And there you also see some submarine creature in the bottom right that is living on this little pillow lava there. And life, as I said, is coming very quickly. It's amazing how quickly these rocks are colonized after eruption. And here you have different creatures living there. I'm not good with these animals. I'm good with the rocks only. And so I will not give you details on what they are, but I'm fascinated by it, I have to admit. So, and one of the intriguing discoveries in the 90s was that some people were saying, oh, could there be Atlantis down there? It seems that there's structures and building and architecture down there. Well, it turns out that these are actually just drained lava tubes, and sometimes you get pillows in those when there was water rising up a little bit, and these are actually natural rock occurrences. This is not Atlantis. So if you look at some of these roofs, like the specimen in the bottom right, there you see that when the lava was inside, it was inflating. We talked a little bit about inflation. And then you have these lava strings being pulled apart, and that's very good evidence for that. And this is not a human construction. It's a very natural phenomenon. Once the lava drains out, we get these pillars staying proud, and sometimes the roofs collapse. It looks like architecture, but it's nature. We talked a little bit about these geothermal springs, and they're quite common, and this is hot water that is emitted, hot water from deep inside that has been heated by the magma sources, and when it does so, it leaches a lot of metals, for example, and when the hot water hits the cool seawater, then it starts to precipitate. It loses its load-carrying capacity, and we get precipitation of minerals. The ocean water is usually also alkaline, while the geothermal waters are acidic, so there's also a pH gradient, there's a chemical gradient between these two liquids, and the water that comes out will suddenly be in a cold environment and in a chemically different environment, and this forces the geothermal waters to precipitate their mineral load. When you have a lot of metals, these are dark. When you have a lot of silicates, these are more white. This is like the white silica mud that you get in the Blue Lagoon. And then we built up these little chimneys because the minerals sink down and they grow together. And we have these fields of chimneys at the ocean floor in those rift valleys. And there is a lot of life coming again very, very quickly. It's warm there, it's cozy, I think, and a lot of animals start to cluster around. And in fact, scientists have recently found some very strange creatures there, the archaeobacteria. Technically, they're not bacteria, they're single-celled living creatures, the archaea, and they are some of the simplest forms of life that we ever found, and they love hot springs. And there's loads of them on the ocean floor. You can risk a speculation that this may have been the very origin of life. People claim meteorites may have done it. I'm not big into meteorites. I think volcanoes have done it, of course. So here's a little impression, an artist's impression on the right-hand side of how these creatures look like. And they love temperatures of about 190 degrees Fahrenheit. And they also love really acidic conditions. Things we don't like so much, they love. So, having looked at the spreading center, I would like to look a little bit at the margins of the Atlantic as well. So we've been here in the center where the red area is, but let's look at the margins. Well, there is a lot of passive margins, as geologists call it, meaning not a lot is happening at the margins. And these passive margins, however, they have often instabilities in form of landslide. There's no volcanoes there, but when the Atlantic spreads, and maybe you have an earthquake every now and then, you may get some landslides there. And some of these landslides can be pretty big. There was a rather large landslide during the end of the last glacial maximum off the coast of Norway, and some of you will actually sail up the coast of Norway, and the historical landslide happened there, and it produced probably a big tsunami. And we can find tsunami evidence all over Scotland and the Orkneys and Shetland. And the historical landslide there in this little map, it's given in red, was going tens and literally hundreds of kilometers into the abyssal part of the ocean. This would have happened approximately 6,000 years ago. 6,000 years BC, so about 8,000 years ago. We're estimating that 3,500 cubic kilometers of debris was shed. This is pretty much the size of the very biggest volcanic eruptions we ever had on the planet. The Toba eruption was about this size. So this is a lot of rock that is moving, and of course a massive tsunami wave would likely have resulted from that. And you can find tsunami deposits in many places. On the map there's little numbers here, 14 meters, 20 meters, etc. So this is the altitude of the tsunami deposits in these different places. Another feature I pointed out earlier is subduction. Subduction is a process that is very common in mature oceans, but the Atlantic is not very mature. The Ring of Fire, for example, is where the plates, the oceanic plates, are subducted. They sink into the Earth mantle under their own weight if they're old enough. If they're younger, but there's a continent, they're pushed under it, like in the Andes. There's a forceful subduction. If you have old rocks, it's going to be a voluntary subduction. At the age of about 185 million years, oceanic plates tend to be so cold and thick and dense that they will happily sink into the mantle quite by themselves. And this is what we're seeing in just a tiny spot in the Atlantic. There's one place where the ocean crust is that old, where it's actually about 185 million years, and there we're starting to see subduction. So this is a sign of maturity for a good ocean, and the Atlantic is just about showing the first signs of that, and that's in the Antilles and the Caribbean. There we have a string of subduction zone volcanoes. They tend to be a lot more explosive than plume-type volcanoes or ridge-type volcanoes, because they bring a lot of water down into the source of the magma, and that makes the volcanoes rather unpleasant. We had the deadliest eruption of the 19th century at Martinique, Montagne Pelée, 1902, 36,000 people dying. No such thing has been seen, for example, on Hawaii. So this gives you a flavor of this, and there the string of islands, Guadeloupe, Martinique, etc., Dominica, these are all little subduction zone volcanoes that have started to form an ocean chain. So I want to give you a flavor here of how this looks, and the diagram on the right is very complicated. This is from a recent scientific paper where they are summarizing all the details, but there we have the Atlantic plate being pushed under the Caribbean plate, and as a result we get these initial strings of oceanic volcanoes, and ultimately they will make an arc like in Indonesia or in Japan. And as I said, this is the only place in the entire Atlantic where this happens, and this is the sign that, well, the Atlantic is just about getting ready to be a proper ocean. So, having talked about subduction and ridges, quick word also about plumes. And plumes and hotspots, I mentioned them before. The Atlantic is actually littered with them, and there must have been some ancient, long-lost continent that sits somewhere under the Atlantic, and it produces a lot of heat down there, and then we get these little, well, areas where hot rock is rising up, and it's out of nowhere, and it produces these little island clusters like the Cape Verde Islands, the Canary Islands, Madeira, the Azores, and of course also Iceland. If we go further down into the southern Atlantic, we have Tristan, we have Ascension, and all of these are actually little geochemical anomalies that sit in the central parts of plates, and they're not related to spreading or subduction. So here, to give you a little bit of evidence, in the top right-hand side, there's the Canary Islands, and the magnetic anomalies are given in yellow, but the age of the islands is given in blue there, and they are crossing the magnetic anomalies, implying that they have nothing to do with ocean spreading. They're really oblique to it. We have many of those little plumes, and in the map in the lower right, you see these tiny little yellow dots and the red lines. These are strings of oceanic plume-type volcanoes, and of course, Iceland is there as well, amongst others. So, when we go to the South Atlantic, we shouldn't forget it, although we are in the north, of course, but there we have Tristan da Cunha, and Tristan da Cunha has a whole submarine string of little volcanoes, and they are connected to that. On the other side, which is not on the map, we have the Rio Grande rise, which is also part of this, and the idea here is that we have these rising hot rock masses, plates moving above, and then we get these strings of little submarine volcanoes that sometimes make islands. So when we look at these kind of situations, there's one place where we actually have, in the North Atlantic, where we actually have plumes and the ridge coming together. That's Iceland. But there's actually one place where we have three plates coming together, and we have a plume on top of that. It's a very special place, and that's the Azores. The Azores are actually the triple junction between the North American plate, the Eurasian plate, and the African plate. And there we have a hell of a lot of earthquakes. This is all the little dots on this map. These are earthquakes. And the Canaries don't have a lot of earthquakes, but the triple junction that forms the Azores area, that has huge amounts of earthquakes. So personally, I think, well, I wouldn't buy a house on the Azores. But it's up to you. So it's not a good place, and just about half a year ago, there was a volcano scare. It did not lead to an eruption, but people were very worried, and there's some big earthquakes in the Azores, because here it's not just a plume. We actually have 3 continents meeting there, a rare place, and geologically highly interesting, but maybe not a good retirement place. So the Azores are also characterized by a lot of fractures and faults, and the islands there are really elongate. They form along these faults, and I tell you, islands that are elongate, they are dangerous. So think about this when you think about buying some property somewhere in a remote place. So we had now rifts, the spreading centers, we had plumes, hotspots, and we had subduction, and as I said, good old oceans like the Pacific, they do this for millions and millions of years. The Atlantic is only developing the first subduction zones now. In the geological future, however, we will likely have subduction zones all along the Norwegian margin, the British Islands, Ireland, and the, well, Spanish part, the France, and all around the Eastern African side as well. Sorry, the Western African side. And of course, on the other side of the ocean as well, where we have Brazil, for example, and the East US seaboard. All of this will, in the geological future, become subduction zones, like the Ring of Fire. And this is actually one of the key exam questions that was frequently asked in Trinity College, I remember. You had to write a 3-hour essay on what is the geological future of Ireland. And the answer is, it will be an explosive subduction zone.